Hi, welcome back. One of the simplest tasks to perform in cleansing is to identify incompleteness and to decide how to deal with it, which means to recognize the missing values and assess its impact on the quality of the information discovered. A missing value exists whenever we have some record where one or more of its describing variables don't have any value assigned. Missing data is mostly due to problems during the collecting phase, with some equipment and sensors malfunction, data that is not collected since it doesn't apply in that situation, or just that someone didn't consider it important at the time. After identifying the missing values, we need to decide what to do next, since most recent implementations of mining techniques are not able to deal with data incompleteness. For example, none of the Python scikit-learn methods do it. Basically, we have two choices: to ignore any record with a missing value by dropping it from the dataset, or to fill it with some value. Both choices have their disadvantages. For example, in the presence of too many missing values, discarding the records may remove most of the data, making the information discovery impossible. But filling them with the wrong choice also can impair the discovery depending on its goal. There are several choices for filling a missing value: a new value for standing for it, the mean, median or mode value, the conditional mean value, or the most probable value, to name a few. Next, we are going to explain each one through an illustration based on a new version of the IRIS data. If you remember, the IRIS dataset has 150 records of flowers of three types. Imagine that there are some missing values in some of its records, as shown in the table. Its identification is trivial, and we find 3 for sepal length at 8th, 16th and 18th row, 1 for sepal width and petal length for records 11th and 16th, respectively, and 2 for petal width on the 6th and 16th. Our first choice is to ignore the record in the 16th row, since 3 of the 5 variables are missing, and so the estimation of all its values would be too risky. Otherwise, we have some choices to fill the missing values. The first one is just choosing a value for expressing the incompleteness, which is the more obvious choice, and the usual values are something like unknown or NA, standing for not available. This works when the number of missing values is considerably low, or when the inexistence of some values may reveal any important information. For example, the cases where some data is not collected since the variable doesn't apply. In our cases, we use the NA value to fill all missing values but the ones on the discarded record. The most common choice, however, is to input the mean value for the variable or its median or mode. In this case, we do not harm the data distribution, but usually the variable becomes less relevant to express any information. In the flowers case, we would fill both missing for sepal length variable with 5.84, since it is its mean value, as we can see in the 5 summary measures for each one of the variables in the chart on the right. The missing on sepal width would be filled with 3.05 and 1.20 on petal width. Another possibility aligned with the earlier one is to fill the voids with the mean or mode for the variable, but conditionally to some other variable, for example, the variable we are trying to model. And so, for our dataset and conditioning the data in order to the IRIS class, the first missing would receive the value 5.01 since it corresponds to acetosa, and 5.84 for the second since it is a virginica. 3.42 would be assigned for the missing sepal width and 0.24 for the petal width, both setosa flowers. The last approach is the most interesting one, since it would choose to input the most probable value to fool the missing. However, estimating this value is non-trivial and encompasses some level of risk. This estimation can be made just by looking at the other values the variable takes for the rest of the dataset, but this is only possible if the data could be sorted along with some other variable, such as time, for example. In our case, we could sort the data according to sepal length in order to estimate the value for sepal width, which should assume a value around 3.2 since there are other records in the dataset for the same sepal length with such width. The alternative, if there is no such order, is to train some model for the variable using the rest of the variables, for example, through regression or other predictive techniques. So, for our dataset, and since by now we know that the petal variables are highly correlated, we are able to estimate the missing value through the line found with linear regression, and our missing petal width in the 6th record would be estimated to be 0.18. Note its closeness to the other records with similar petal lengths, where their width ranges from 0.1 to 0.3. However, when the correlation among the variables is weak, this approach is not feasible, as you can see in the chart on the right. In these cases, if there is other information that can help, we can make use of it and apply the estimations to subsets of the data. For example, we already know that there are better levels of correlation for the sepal variables if conditioned to the class. So, we create regression estimations for each class and estimate the missing values. However, there is an important issue here. We are using the class label. If its prediction is our learning target, like for classification, this will be unknown for non-observed records, and so we need to be very careful when choosing the constraints to create the estimators. If we don't know to which class belongs a record, we are not able to choose among the estimators for filling the missing value. See you in the next video.